Okay, so we're going to talk about the difference between scientific notation and significant figures, because I'm petty and I want to prove a point. And also, education is good.
Just go.
Excuse you. Anyway, so scientific notation is like you have a number that's like 0.0000034, and you don't actually want to write all those zeros because they're dumb, and all you really care about are these two numbers right here. So you can write 3.4 times 10 to the, how many is this? 1, 2, 3, 4, 5, 6, 7 times 10 to the -7, and this is the same thing as this. And this is just the faster way to write it, and because science deals with a lot of numbers that are either really, really small if you work in chemistry or really, really big if you work in physics, this is way easier to write than, say, 34 billion. Million, that's million. Billion. Over and over and over again. See what I'm saying? This is faster than this. So this is called scientific notation because in science, it's used a lot. And also in other forms of math, but it's scientific because it's science anyway. Scientists are dumb and lazy. That's what I have learned in science. Significant figures is also a science thing. So if we take this number over here, 0 point, how many zeros? 1, 2, 3, 4, 5, 6, 3, 4. If you were to measure something, and this was the result that you got, do you know how many significant figures you have? You have 2. That's a lie. You don't have 2. Yes, you do have 2. Becca, how many 2s do you have?
You only have 2 because
You only have 2.
those ones are after the decimal and not after a significant figure.
Fair. So, significant figures are a way to measure how accurate your measurement is, if that makes sense. So, say you have a ruler, and your ruler measures 1 centimeter, 2 centimeters, 3 centimeters, and there's no little lines in between. If you were to measure a pencil, like so, you would say guess around, like 2.3-ish, but because there's no measurements in here, you can't be certain what the 2.3 is, and so you can for sure say it's over 2 centimeters, but you can't really guess in here, and so you get one guess place, and that's 2.3. And so then, if you were to do math and say this pencil plus the length of a pen, let's put a pen cap on this pen, yeah, which we know this pen is exactly 2.346 centimeters. If you were to say add the lengths of these two things, 2.3 plus 2.346. They're the same number. Oh, never mind. I wrote that. And you add them together, the math answer would say, what is this? This is 4.646. That is what you get if you do the math. However, because you don't actually know the exact length of this particular pencil, you can't say with this amount of accuracy that the length of these two things is equal to this. You only have up to this amount of accuracy, so you can't count these two. And so then you have 4.6 because, in addition, you have as many places past the decimal places as you have. If we were multiplying them, then you would only have 2 because you have 2 significant figures here.
Can you wrap this up?
Yeah. So, in conclusion, significant figures is a measurement of accuracy, whereas scientific notation is a way to write really large numbers or really small numbers. And the overlap here is that if you have a really, really large number, but you only know it to so many significant figures, like if you have 2, 3, if you have this, you only have 2 significant figures that you can work with because these zeros don't count because they're placeholder zeros. And so then you would write it in scientific notation because you don't care about these zeros. They don't matter. And so you would still say 2.3 times 10 to the 1, 2, 3, 4, 5, 6 times 10 to the 6. And this is in scientific notation, showcasing how many significant figures you have. So they are different, but they are similar, and they work very well together. End of story.